Hello all, welcome to this video on Networking Lab. Today I'll be talking about NS2 using a simple program. To prepare for network changes, network engineers need to test how those changes can affect network function. However, experiments on the production network can result in service problems and create downtime, necessitating the use of network testing labs. In some cases, engineers test in network labs built with the same equipment used in the production network, but not always. When network engineers can't use a real replica of their network, they turn to network simulation and network emulation. While both are similar in that they both replicate network environments, they use different approaches. Network simulation tools create models of a network's full stack of technologies, including network devices like routers and switches. They configure these models in different methods and deal with different traffic protocols in specified ways. They enable engineers to test network configuration and topology changes, as well as their effect on other devices and application traffic flows. They can touch all network layers from layer 1, the physical layer, to layer 7, the application layer. Network emulation tools are boxes that pretend to be entire physical networks. Systems, often one or two test servers and a test client, connect to emulators to test how applications work when faced with the performance artifacts inherent to any production network. Areas of analysis network administrators need to test include the following: latency, jitter, packet loss, congestion, packet collisions, etc. These tools touch layer 1 and layer 2, which is the physical layer and the data link layer. Network engineers and developers can tune the emulation to test against a range of network performance profiles, whether excellent or poor. It configures emulators to mimic characteristics of different kinds of networks. Now we look into the history of NS. NS is a discrete event simulator targeted at networking research. It provides substantial support for simulation of TCP, routing, and multicast protocols over wired and wireless networks. It began as a variant of the Real Network Simulator by S. Keshav in 1989. NS2, which is the discussion of this class, is a discrete event simulator where actions are associated with events rather than time. An event in a discrete event simulator consists of execution time, a set of actions, and a reference to the next event. Unlike a time-driven simulator, in an event-driven simulator, time between a pair of events does not need to be constant. When the simulation starts, events in the chain are executed from left to right chronologically. Currently, NS development is supported through DARPA with Summon and through NSF with Concert, both in collaboration with other researchers including ACI-RI. The first version of NS, known as NS1, was developed at Lawrence Berkeley National Laboratory, which is LBNL, in the 1995-97 timeframe by Steve McCann, Sally Floyd, Kevin Fall, and other contributors. This was known as the LBNL Network Simulator. NS2 began as a revision of NS1. In 2000, NS2 development was supported through DARPA with Summon and through NSF with Concert, both at USC/ISI in collaboration with other researchers including ACI-RI. Now we'll see some features of NS2. It is primarily Unix based. It uses TCL as its scripting language. It has object-oriented support, which is through OTCL, and it has support of TCLCL, which is the C++ and OTCL linkage. Two graphical representations are used in NS2. One is NAM, which is Network Animator, and the other is xgraph. NAM displays how the different nodes are communicating and how the exchange of packets has been done. It shows the topological design of network that is simulated. Xgraph is another method that represents the results in the form of a graph. It saves the result in a trace file. Now we'll see some of the disadvantages of NS2. Classless inter-domain routing and subnetting are not provided by the NS2 simulation. When the network is too large, that is when the number of nodes increase, then there is infinite weight and NS2 cannot give satisfactory results of such large simulations for NS2. It has split object model which consists of OTCL and C++ and the use of TCL. There is a large amount of abstraction at the network layer and below, which leads to big discontinuities when transitioning from simulation to experiments. One of the main problems of NS2 is that to extract the results, we need to parse the trace files, and the tracing system in NS2 is not easy to use. In 2003, a team led by Tom Henderson, George Riley, Sally Floyd, and Sumit Roy applied for and received funding from the US National Science Foundation, which is NSF, to build a replacement for NS2 called NS3. This team collaborated with the Planet project of INRIA at Sofia Antipolis and formed a new open source project. In the process of developing NS3, it was decided to completely abandon backward compatibility with NS2. Development of NS3 began in July 2006. It is built using C++ and Python with scripting capability. NS4 is a P4 driven network simulator and the first research effort on applying P4 to network simulation. P4 is a high level, domain specific programming language for describing behavior of protocol independent packet processors. It is used to define how switches process the packets, no matter what type underlying hardware is. NS4 design consists of control plane and data plane. NS4 allows network simulation for Bluetooth, 802.11a, CSMA, LTE, etc. Next is the NS2 architecture. NS2 consists of two key languages, which is C++ and OTCL, which is the object-oriented tool command language. While C++ define the internal mechanism, that is the backend of the simulation objects, the OTCL will set up simulation by assembling and configuring the objects as well as scheduling discrete events. The C++ and OTCL is linked using TCLCL. There are two output files, a file with .nam as extension to show the animation and a file with .tr or .xg or any other as specified to plot the graph and to identify the performance characteristics. To see the graph, we can use xgraph or trace graph or GNU plot. The trace file can also be processed using AWK script by analyzing the text information from the file and by predicting the performance of the network. This is the NAM file and the graph, which is the output of the TCL simulation script that goes through NS2. TCL or Tool Command Language is a scripting language that is mainly deployed in the specification of protocols along with the application. TCL casts everything into a mold of a command, even programming constructs like variable assignment and procedure definition. All operations are commands including language structures. They are written in prefix notation. Some of the tools for generating TCL script for NS2 are NS2 Scenario Generator or NSG, which is a Java-based tool that generate TCL scripts for wired and wireless scenarios for NS2. Visual Network Simulator or VNS, which is a tool that provides support to differentiated service scenarios. NS2 Workbench, which makes NS2 simulation development and analysis faster and easier for students and researchers without losing the flexibility or expressiveness gained by writing a script. And finally, Network Simulation by Mouse or NSBM, which is developed in Java, which is a graphical tool that is used to generate TCL script using a mouse. Nodes and links can be created with a single mouse click. OTCL is an extension to TCL or TK for object-oriented programming written in C++. NS2 is actually an OTCL programming language interpreter consisting of built-in library of network simulation objects. By adding object definitions in C++ source code, OTCL library of objects can be extended. OTCL can run on platforms like Unix, Windows, Solaris, etc. Here C++ runs in the background and usually deals with the implementation of queues, protocols, packets, agents, applications, etc. TCLCL, which is the TCL with classes, is a TCL or C++ interface which is used by MASH, VIC, VAT, RTP Play, NS and NAM. It provides a layer of C++ glue over OTCL. NS2 uses OTCL to create and configure a network and use C++ to run the simulation. All the C++ codes need to be compiled and linked to create an executable file. Now we'll look into simulation trace file. The trace file is defined as the auto-generated result of NS2 simulation. The simulation file is stored in both .tr and .nam file formats. NS2 currently supports a number of different types of trace files. Traces and monitors represent the only support for data collection in NS2. Traces record events related to the generation, enqueuing, forwarding, and dropping of packets. Each event corresponds to a line of ASCII characters which contain information on the event type and the information stored into the packet. NS2 provides three kinds of formats for wired networks, which is tracing, monitoring, and NAM trace file. Let us move to see the tracing. So the trace string will consist of 12 fields. We'll see what each field stands for. The first field, which is the event field, will tell us what kind of event has happened. So plus means add to queue. If it's a negative sign, it is to remove from the queue. D means the packet is dropped. R means the packet is received. The second field is the time field, which is used to indicate the time at which the event occurs. Then there is the from node and the to node used to specify the sender and receiver of current package. Then we have the packet type, which is the fifth field that is used to represent what type of packet is going through right now. Can be FTP, CBR, HTTP, or AODV packet, which is ad hoc on demand distance vector packet. Then there is packet size, which is used to show the packet size in bytes. Then there is the flags. So there are 7 flags here. So each flag we'll name. The first one is disabled flag. Second one is ECN echo, which is C flag. Third, priority in IP header is enabled using P flag. Then there is TCP fast start, which is the F flag. Congestion action, which is A flag. Congestion experienced, which is E flag. Explicit congestion notification is on, which is N flag. Then there is the flow ID, which provides the IP flow ID as per the IP version 6. Then we have the source and the destination address. So that will be specified as address.port. Then there is the sequence number here, which is the agents attach sequence number with packets, and finally the packet ID, which is a unique identifier for each packet. Now this is the sample trace file here. As specified, we have all the events marked here, either as plus minus D or R, followed by the time, then the from node, the to node, type of packet, packet size, then there is the flag bits, the flow ID, source address, destination address, sequence number, and then finally the packet ID. Monitoring is a useful tool to find detailed information about queues. A queue monitor tracks packet arrival, departure, drop statistics, and may optionally compute averages of these values. Then there is the NAM trace file. So the NAM trace file should contain topology information like nodes, links, queues, node connectivity, etc., as well as packet trace information. A NAM trace file has a basic format to it. Each line is a NAM event. The first character on the line will define the type of event and is followed by several flags to set options on that event. There are two sections in that field, which is the static initial configuration events and the animation events. All the events that starts with hyphen T star in them are configuration events and should be at the beginning of the file. By using NS2, we can generate packet traces both in .tr and .nam files. .tr files are in the text-oriented format. Using the .nam trace file, we can get the network animator result. So we can see the hyphen T star events, which are all configuration events. We can also identify some lines of the instructions here. So these two lines are used to set the color of the packet flow. And then this is the set of lines that is used to set a label to each of the nodes. This is the line that sets the position of the nodes in the NAM animator. And these two lines define the shape of the nodes. Xgraph in NS2 is used to plot the network parameter characteristics like throughput, delay, jitter, latency, etc. Xgraph is an X Windows application that includes interactive plotting, graphing, animation, etc. AWK scripts are deployed to process the data from NS2 trace file that is stored along with the file extension .tr. In addition, the AWK file in NS2 is deployed to calculate the performance metrics such as consuming energy, end-to-end delay packet delivery ratio, throughput, etc. To conclude, NAM provides visual interpretation of overall network. It executes from TCL script directly. It provides controls for play, stop, pause, display, speed controller, packet monitor facility, etc. It supports for drag and drop interface for creating topology. This is how the NAM console looks like with the nodes and the links. Speed controls are available here. We'll see details of this in the demo portion. NAM graph shows the overall graphical representation of packet flow, that is, when the packets are received or dropped. NAM files contain the workflow of TCL script. Queue management is defined as the algorithm that manages the length of the packet queue by dropping the packets when necessary. From the point of packet dropping, queue management can be classified into two types. One is the passive queue management, where the packet drop occurs only when the buffer gets full, for example, drop tail. Then we have active queue management, which employs preventive packet drops. It provides an implicit feedback mechanism to notify senders of the onset of congestion. Arriving packets are randomly dropped. Example, RED. In drop tail, packets are dropped from the tail of the queue. Once the buffer gets full, all the arriving packets are discarded. Packets already in the queue are not affected. Then there is red or random early detection. It accepts all packets until the queue reaches the minimum, after which it drops a packet with a linear probability distribution function. When the queue length exceeds max, all the packets are dropped with a probability of 1. Then there is weighted random early detection, which is a queuing discipline for a network scheduler suited for congestion avoidance. It is an extension to RED, where a single queue may have different sets of queue thresholds. Each threshold set is associated with a particular traffic class. Now we will see the basic TCL commands. So an NS script starts with making a simulator object instance. A variable NS is being initialized by using the set command. Here in the code, this new simulator is an instantiation of the class simulator which uses the reserved word new, which is given here. So we can call all the methods present inside the class simulator using the variable ns. To declare variable in TCL, set command is used. So set command will create a variable and assign a value to it. Format is set, variable name and variable value. This is an example of such a code. Set n0 and this is the variable value. The simulator object has member functions that enable the creation of the nodes and define the links between them. The class simulator contains all the basic functions. Since ns was defined to handle the simulator object, the command $ns is used for using the functions belonging to the simulator class. Now, what happened here is the event scheduler object creation. Now, this command $ns color FID color is used to set the color of the packets for a flow specified by the flow ID. This member function of simulator object is for NAM display and it has no effect on the actual simulator. This is a sample code where the color of the flow ID 1 is set as dark green. Some of the available colors are black, blue, violet, red, yellow, magenta, etc. The next command $ns nam trace all space file descriptor is used when, in order to have output files with the data on the simulation or files used for visualization, we need to create these files using the open command. That is given in these lines of code where we are creating a data trace out.tr and a NAM visualization file which is out.nam. Both are opened in write mode. Within the TCL script, these files are not called explicitly by their names but instead by pointers that are declared as NA and NF respectively. This member function tells the simulator to record simulation traces in NAM input format. It also gives the file name that the trace will be written to later by the command $ns flush trace. Similarly, the member function traceAll has a parameter, the name of the file where the traces will go. With this simulator command, we trace all the events in a specific format. Next, we will see the function proc finish. So here, all the post-simulation processes are specified. A sample code is given here. Here the word proc defines that it is a procedure. The name of the procedure is finish and it doesn't have any arguments. The word global means that we are using variables declared outside the procedure. The TCL command close closes the trace and NAM files defined before. The TCL command exec executes the NAM program for visualization. So here the name is directly given and the ampersand stands for the address of animation file. Here we see that we pass the real name of the file of traces to NAM and not the pointer because it is an external command. Then there is the command exit, which ends the application and returns the number 0 as the status to the system. 0 is the default for a clean exit. Other values can be used to say that this is an exit because something failed. At the end of the NS program, we should call the procedure finish and specify at which time the termination should occur. For example, here at time 3 second, the finish procedure is called. The at of the simulator allows us to schedule events explicitly. The next command $ns duplex link or simplex link node 1 node 2 bandwidth delay queue type. It is used to create simplex or duplex link of specified bandwidth and delay and connects the two specified nodes. In NS2, the output queue of a node is implemented as part of a link. Therefore, the user should specify the queue type while creating the links. Here we have two examples. This is a simplex link between node 1 and 2 with bandwidth 2 MB, 10 millisecond delay and drop tail queue management. Then we have a duplex link between N2 and N3 with bandwidth 1.7 and delay 20 millisecond with the queue management which is drop tail. So here drop tail is used. If you want to use the RED queue, we can replace drop tail with RED. Like a node, a link is a compound object and users can create its sub-objects and connect them and the nodes. One thing to note is that we can insert error modules in a link compound to create a lossy link. Here users can make and insert any network objects. The next command $NSQ limit node 1 node 2 number. This line sets the queue limit of the link that connects node 1 and node 2 to the number specified. So here the queue limit between N2 and N3 is 10. Now that the basic network of setup is done, the next thing to do is set up traffic agents such as TCP and UDP, traffic sources such as FTP and CBR, and attach them to nodes and agents respectively. For data to be sent here, we need two layers, which is transport layer protocol consisting TCP UDP and application layer protocol which has FTP. CBR is a class of service. Agents are used to separate protocol states from nodes. They are always associated with nodes. An agent has a name which is a unique identifier of the agent. It is shown as a square with its name inside and a line link that square to its associated node. A null agent just frees the packets received. A TCP sync agent generates and sends acknowledgement packets to the sender, which is a TCP agent, and frees the received packets. The command set TCP new agent or TCP shows how to create a TCP agent. In general, users can create any agent or traffic sources in this way. Agents and traffic sources are in fact basic objects, not compound objects, mostly implemented in C++ and linked to OTCL. Therefore, there are no specific simulator object member functions that create these object instances. To create agents or traffic sources, a user should know the class names of these objects, which is agent slash TCP, agent slash TCP sync, agent slash FTP, application slash FTP, and so on. Now, TCP is used to provide a reliable transport of packets from one host to another by sending acknowledgement on proper transfer or loss of packets. Thus, TCP requires a bidirectional link in order for acknowledgements to return to the source. The command set TCP new agent slash TCP gives a pointer called TCP to the TCP agent object of NS. The command $NS attach agent $N0 $TCP will define the source node of TCP connection. The next command, set sync new agent slash TCP sync, defines the destination of TCP by a pointer called sync. The next command, $ns attach agent $n1 $sync, defines the destination node as n1. This procedure is shown here. N0 is defined as the TCP source and N1 is defined as the sync. The next command, $ns connect $TCP $sync, makes the TCP connection between the source and the destination, that is N0 and N1, that is shown here. After the two agents will communicate with each other, the next thing is to establish a logical network connection between them. So this line establishes a network connection by setting the destination address to each other's network and port address pair. When there are several flows such as TCP, UDP in a network, to identify them, we set their flow ID by using the command $TCP set FID underscore space 1. Now the default packet size of TCP is 1000 bytes. Now we'll define FTP over TCP. FTP is a standard mechanism provided by the internet for transferring files from one host to another. FTP differs from other client-server applications in that it establishes two connections between the client and the server. One connection is used for data transfer and the other one is used for providing control information. FTP uses the service of TCP. The well-known port 21 is used for control connection and the other port 20 is used for data transfer. The command set FTP new application slash FTP gives a pointer called FTP, which indicates the FTP application. Next, we attach the FTP application with TCP agent as FTP uses the services of TCP, which is done by $FTP attach agent $TCP. That process is shown in this diagram. And we have another attribute called set type. The set type is given as FTP. Then we have UDP. So user datagram protocol is one of the main protocols of the Internet protocol suite. UDP helps the host to send messages in the form of datagrams to another host which is present in a Internet protocol network without any kind of requirement for channel transmission setup. UDP provides an unreliable service and datagrams may arrive out of order, appear duplicated or go missing without notice. UDP assumes that error checking and correction is either not necessary or performed in the application, avoiding the overhead of such processing at the network interface level. Time-sensitive applications often use UDP because dropping packets is preferable to waiting for delayed packets, which may not be an option in a real-time system. Here the command set UDP new agent slash UDP gives a pointer called UDP, which indicates the UDP agent, which is an object of NS. Then the command $NS attach agent $N0 $UDP defines the source node of the UDP connection. The next command set null new agent slash null defines the destination of UDP by a pointer called null. These processes are shown in this figure where N0 is the UDP source and N1 is the null. That is the destination. The next command $NS attach agent $N1 $null defines the destination node as N1. Next the command $NS connect $UDP $null makes the UDP connection between the source and the destination, that is N0 and N1. To identify a particular flow, we mark it using the command UDP set FID underscore 2. Then there is CBR or constant bit rate. It is a term used in telecommunications relating to the quality of service. When referring to codecs, constant bit rate encoding means that the rate at which the codec's output data should be consumed is constant. CBR is useful for streaming multi-data or multimedia content on limited capacity channels since it is the maximum bit rate that matters, not the average. So CBR would be used to take advantage of all the capacity. CBR would not be the optimal choice for storage as it would not allocate enough data for complex sections while wasting data on simple sections. Now we'll set CBR over a UDP connection. So here CBR is attached to UDP and this line will create a connection between N0 and N1, a logical connection. We'll define a CBR connection over a UDP. So we have already defined the UDP source and UDP agent similar to TCP. Instead of defining the rate, we define the time interval between the transmission of packets in the command $CBR set rate as 1 MB. Next, with the help of command $CBR set random underscore false, we can set random noise in CBR traffic. We can keep the noise by setting it to false, or we can set the noise on by the command $CBR set random underscore 1. We can set packet size by using the command $CBR set packet size 1000. Packet size is specified in bytes. The command $NS attach agent node agent. The attach agent member function attaches an agent object created to a node object. Actually, what this function does is called the attach member function of specified node, which attaches the given agent to itself. Similarly, each agent object has a member function called attach agent that attaches a traffic source object to itself, which is shown here. The command $NS duplex link op $N2 $N3 queue position 0.5. Here the queue position is defined as the angle of the queue line with the horizontal. This command here $NS at 0.0 $N0 label src1 will assign the label src1 to node 0. The command $N0 color blue will set the color of the node N0 as blue. The command $N2 shape hexagon or square will set the shape of the node N2 as hexagon or square. Assuming that all the network configuration is done, the next thing to do is write a simulation scenario or simulation scheduling. The simulator object has many scheduling member functions. However, the one that is mostly used is $NS at time in double quotes string. This member function of a simulator object makes the scheduler to schedule the execution of the specified string at a given simulation time. For example, $NS at 0.1 $CBR start will make the scheduler call a start member function of the CBR traffic source object which starts the CBR to transmit data. In NS, usually a traffic source does not transmit actual data, but it notifies the underlying agent that it has some amount of data to transmit. And the agent, just knowing how much of the data to transfer, creates packets and sends them. After all the network configuration, scheduling, and post-simulation procedure specifications are over, the only thing left is to run the simulation, which is done by $NS run. Now we'll look into the code that is used here. First, we'll create a simulator main class object, which is using the command setNS new simulator. Then we define the colors for data flows. $NS color 1 as green, color 2 as orange. Then we open the NAM trace file. We've already seen these statements before. And this is defining to where all the NAM trace file information should be written to, and this defines where all the trace file information should be written to. They are referencing to the corresponding NF, that is the NAM file pointer, and NA, which is the trace file pointer. Then the finish procedure is defined, which has three parameters, that is the name of the procedure, the parameter of the procedure, and the beginning of the procedure. Then the code of the procedure is written. After it, we create the four nodes we are going to use here, N0, N1, N2, and N3. Then we create the links between them. One is simplex, the others are duplex links. All of them use the drop-tail queue management method. Then the queue size is set to 10 for the queue limit between N2 and N3. Then we can set the position of nodes in NAM. We have already looked into the format of it. So it is done by $ns duplex link op, specifying the two nodes and followed by the orient word, after which we specify the position as right down or right up or right. Then we are assigning three different labels, four labels for all the four nodes. So labels can be defined in different formats. The format I used here is $ns at 0.0 in double quotes. I give the name of the node $n0 followed by label followed by the name of the label. Then the color of the nodes are set as blue, red, magenta, and brown. Then the shape of the nodes. Two of the nodes are circles and one is a hexagon and the other one is a square. Then the queue position is specified here. Then the TCP connection is set up, giving it a flow ID, attaching the agent, defining the sink, attaching it, connecting them. Then the FTP is defined over TCP, connecting the TCP and FTP agents, then setting the type as FTP. Similarly, we set up the UDP connection where we attach the UDP source, then define the UDP sink, connect them, define the flow ID as 2. Then we set up CBR over UDP. There also we set up the agent. We set the type as CBR, packet size as 1000, rate as 1 MB, and random value as false, which means we are cutting off the noise. Then we are scheduling each of these. At 0.1 second, we'll start CBR. At 0.2 second, we start FTP. At second 2.0, we stop FTP. At second 2.5, we stop CBR. And finally, we call the finish procedure at third second. We also print two additional data on the terminal after the execution. So one is the CBR packet size and other is the CBR interval. We have both these parameters here. So the format is put s in double quotes. We write what is to be printed there. CBR packet size equal to, in square brackets we give $CBR set packet size. We also need the CBR interval. So the next line is put s in double quotes. We write CBR interval is equal to, in square brackets, $CBR set interval underscore. Finally, we run the simulation using the command $NSRun. This is a screenshot of the .tcl code, ns.tcl code that I explained before. This is the NAM console. This is how the network looks like with the different colors and shapes. And these are the CBR packet size and CBR interval values that is printed on the terminal. Then I have also written an AWK script in order to extract two fields from the trace string. As we already saw, this is the format of the trace string. So here I have written an AWK script in order to extract the fifth column, which is the packet type, and the 11th column, which is the sequence number. So for AWK script, this is the format. We have a begin section where we write the initialization. Then there we define the patterns and the corresponding actions to be taken. Finally, the end section. So here I am extracting those two fields, and in addition I'm also counting the number of packets that have been dropped. So in the begin section, I'll define a variable C as 0 that is used to count the number of packets dropped. After that, I'll begin the next section where the pattern and actions are defined. So there I give an if condition. If $1, that is the event field, is 1, and if the type is D, that is if the packet is dropped, in curly braces I write C++ to increment the count, and also I'll print the corresponding packet type and sequence number. I'll close the braces for the if condition and the brace for pattern action combination. Then finally I have the end section where I will print the number of packets dropped, which is the value in variable C. Now this is how the output looks like when this AWK script is run on the trace file. So for running AWK script on a trace file, the command is AWK space -f, which stands for the fields to be extracted, and then we specify the AWK script file, which is ns.awk, followed by the trace file, which is out.tcr. We have the packet type and the sequence number. Finally, we have the number of packets dropped as 15. Now we'll see a small demo of how the NS2 works. Now this is how it is going to work. So I have the .tcl file and .awk file. You can see the code of both. This is the .tcl file and this is the .awk file I explained before. And we are running it in the terminal using the ns command ns.tcl. You'll see the CBR packet size and interval, and we have the NAM console opening, and this is the network that we designed using that code. So this NAM console version window should not be closed under NAM is over. So here we have different buttons to control this. We can either zoom in or we can zoom out. We can edit the position. If we click it again, we cannot edit it. Then we have the play button, playing forward. Then we can stop it. Then we can play it again, playing forward. Can play it backward, fast forward, and doing it in the backward direction. So we can also change the step size, make it very slow or fast. So when we play it in the reverse order, it will be playing in the reverse timeline. Here we can see all the nodes have their labels, and you can see the packets are dropped using the drop tail method. So its output will have .nam file and .tcl file. This is the output of the nam file. We have already discussed its format, and this is the .tr file over which the AWK script is going to be run. So we are looking for packets which are dropped. So we are taking the fields whose event type is D. So we'll search it here. So for the particular D, we'll take the packet type and the sequence number, $5 and $11. So we'll execute it using the command we specified, awk-f ns.awk out.tr. Then this is the output we receive. If the file is too large, we can store it into a different file instead of displaying it. So for that, we can run the same command, write it to another file called maybe analyze. So we have that file created. So when you open it, you'll get the same output there. That's all for now. Thank you for watching.